Assalamualaikum. So the graph continues, and in this session we are going to discuss section number 10.4 of the chapter 10, of course, and which is about graphs. So let's see what's in store for us in this section. So this section is about connectivity. So we'll see different ways to connect graphs, vertices and edges. So section summary. First of all, we'll define a path in a graph, and then there is a discussion about connectedness in undirected graphs, then connectedness in directed graphs, and then we'll try to count paths between the vertices. Okay, let's start with the informal definition of a path. Well, a path is a sequence of edges. Okay, it actually consists of edges and vertices, of course, because whenever there is an edge, there are vertices as well. So, path is a sequence of edges that begins at a vertex of a graph and travels from the vertex to vertex along edges of the graph. As the path travels along its edges, it visits the vertices along this path, that is the end points of these paths. So if we have a graph like this is a vertex, this is a vertex, similarly we have for example this and this and this. So this is A, B, C, D for example. So a path is a sequence of edges. So let's start with C, A, that begins at a vertex. Of course, we have to begin with a vertex. So let's begin with A of a graph and travels from vertex to vertex. So let's travel along vertex to vertex. Let's move from A to B, then B to C, and if this is the end point of this travel story and travels from vertex to vertex along the edges of the graph. As the path travels along the edges, it visits the vertices along the path. This is the end point. So this is a path from A to C. Okay. So applications of the path are, of course, several applications are there. There are few examples. Uh, so first, determining whether a message can be sent between two computers, or efficiently planning routes for mail delivery, or let's define the path formally. So, a formal definition of a path: let n be a non-negative integer, n be a non-negative integer, and G an undirected graph. G is, of course, is the set of vertices and edges as always. So undirected graph, a path of length n. So there is a length of path as well. A path of length n from U to B, that is vertex U to vertex B in G, is a sequence of n edges E1 to En. So the number of edges used in the path is the length of the path of G, for which there exists a sequence x naught is equal to u, x1, xn minus 1, xn is equal to d. So this is the starting vertex of the path, and this is the terminal vertex of the path. Such that ei has, for I varies from 1 to n, that is for every ei, e1, e2, en, the endpoints xi minus 1 and xi. Okay, a path of length n from U to V in G is the sequence of length of n edges of G for which there exists a sequence of vertices such that EI has the endpoints xi minus 1 xi. So every edge has endpoints as well. So, but every edge has endpoints in between this set. Okay. So this is the formal definition of path. Now next, when the graph is simple, we denote this path by its vertex sequence, that is x0, x1, xn, since listing the vertices uniquely determine the path. Okay, next, a path is said to be circuit if it begins and ends at the same vertex, u is equal to v, and has length greater than 0. Okay, has length greater than 0 and starting from so from the same vertex and ending at the same vertex. So the path or circuit is said to be pass through the vertices and reverse the edges E1, E2 to En. A path set or a circuit is simple. Now there is a simple path if it does not contain the same edge more than once. Okay. So let's see an example. So this is the graph A, B, C, D, E. So it has 4 vertices and 1, 2, 3, 4, 5, 6 edges. Okay. So let's try a few sequences. So this is a sequence A, E. So we have here is a E and then B, C. So let me draw A, E, B, C, and B. So we got back to B as well. So this is a path, of course. This is a path, but this is not a simple path because in simple path does not contain the same edge more than once. So it contains BC more than once. So this is a path, but this is not simple. Okay. So what about the next one? A. Okay, let's draw this. A, E, then A. Okay. D. All right. B. Okay. D, B. Oh, all done. A, E. Sorry. A, E, again A. Okay. So D, D to B, and then B to C. Okay. And then C to A. And there is no connection between C and A. Right? So these two vertices are not connected directly. So this is not a path. This is a path, but this is not simple. Okay. So try next one. E, B, A, D, B, E. So let's start from E. E, B, A. We cannot go to A from B. So this is not a path. Alright. Again, this is not a path. Next. C, B, D, A, E, C. So this is starting from C and this is ending at C. So let's see if it is a cycle. C or a path even. So first we have to check whether it is a path. A, B, D. Yes, we can go to D. D, A. Yes, we can go to A. A to then E. Okay. E to C. Yes, this is a cycle, right? This is a cycle. This is a simple path, and this is a cycle as well. Cycle means circuit. This is a circuit. This is simple, and this is path, of course. Initially it is path, but this path is a circuit and simple as well. Right? So this was the story of the path, circuit, and simple path. So this terminology is already extended to, this terminology is readily extended to directed graphs, and we can uh, do all these procedures, or we can define path in directed graph as well, and we can define circles, circuits, and simple graphs in directed graphs as well. Okay, there is another example. Now, in the simple graphs, graph is basically simple. Uh, A, D, C, F. Now, A, D, C, F is a simple path of length 4. How many edges are used in this path? 4 edges. A, D, DC, CF, FA. Okay. So this is a simple path of length 4. 4 edges are used in the path, so that is why length is 4. So D, E, C, A. Okay. D, E, E and C are not connected. This is not a path because E is not connected to C. Okay. B, C, F, E, B. B, let's start from B. B, C, F, E, B is a circuit of length 4. Okay. So A, B, A, B, E, D, A, D is a path of length 5, but it is not simple path because AB is used twice. So paths in acquaintanceship graphs. So let's see an example. In an acquaintanceship graph, there is a path between two people, two acquaintances. If there is a chain of people, two people are not acquaintance at all, but they are linked by the people. So two people, if there is a chain of people linking these, where two people adjacent in the chain know each other, right? Know one another. But the people we are linking, they don't know each other, or they may know, but they don't know each other in general. If they know each other, they are already connected. Okay, so there is only one edge in that graph. People know each other, or you may say there is a path of length 1. So path of length greater than 1 can be formed if the people don't know each other, and we can link them by a chain of people linking these people. So where two people adjacent in the chain know one another, in this graph there is a chain of 6 people linking Kamini and Ching. So you can see the chains. Let's start with Kamini to Jan, Jan to Paula. Oh, and where is Ching? Yes, Paula to Todd, Todd to Kamnesh and Ching. How many? Uh, Yes, this is about 6 people. Similarly, we can connect them from any path. Okay? So this is the chain of 6 people linking Kamini and Ching, and this is very important. 6 people linkage. Let's see, 6 degree of separation. So some experts have speculated that almost every pair of people in the world, every pair of the people in the world, whether wherever they are residing and wherever they are living, Two people in the world, every pair of people in the world are linked by a small chain of no more than 6, or maybe even 5 people. Now the play 6 Degree of Separation by John Burke and the subsequent Hollywood movie are based on this notion, 6 Degree of Separation. Okay. So this is important fact about the 6 people chain, what we observed in this example. Next, there is another example. This is the example of collaboration graph. In collaboration graph, two people A and B are connected by a path when there is a sequence of people starting with A and ending with B, okay, such that the endpoints of each edge in the path are people who have collaborated. So, in academic collaboration graph of people who have written papers in mathematics, and the oldest number of a person M is the length of the shortest path between M and the prolific mathematician Paul orders. So, what is the oldest number? So, let me explain. Uh, if I write a paper, or any of the students in the class write a paper. So, what is the oldest? What is your oldest number, or what is my oldest number? How can it be judged? Uh, so, there is a rule for this. Oldest number of a person n is the length of the shortest path, which connects actually M and this scientist, right? So how can we be connected to the person? If I write a paper, if I am co-author of someone, then this is the connection. If my co-author is co-author of another person, this is another connection, and that next co-author is co-author of another scientist, and finally there is a co-author which is the co-author of orders. So, so this is how we can make the graph. We are starting from, for example, Misbah, and there is a co-author, say S of Misbah, and then there is a co-author of S, um, say T of S. So there is another co-author of T, say P, and so on. Finally, this P is, for example, is a co-author of this orders, right? So this is the orders number for me, 1, 2, 3, 4. So this is a path of length 4 between me and this scientist, this mathematician, right? So this is how we can find the orders number, right? And for further knowledge, you can visit the website as well. And there is the table, number of mathematicians with the given orders numbers. So there is the table of so there is orders number 0, there is one person. If someone is not connected with Paul orders anyway, the orders number is 0, okay? And there are 504 persons with orders number 1, and so on. This is the table given in your Becker number. There is another type of collaboration. So this is also an example of collaborative graphs. So in Hollywood graph, so this is Hollywood graph, two actors A and B are linked when there is a chain of actors linking A and B, where every two actors adjacent in the chain have acted in the same movie. Okay, so the Bechdel number of an actor C is defined to be the length of the shortest path connecting C and the well-known actor given diagram. So note that we can define similar number by replacing this actor by a different actor, right? So this is quite similar to oddest number. Uh, so we can again define a connection. We can start with any actor C, and this actor C is connected with the actor D if C and D work together in a film. Okay, so this edge is actually a movie uh, in which they acted together, right? Similarly, if there is an actor E, and ultimately E has worked with this actor, then this is the path of length 4 between C and background. So background number is 4, right? So this is the list given in table number 2 in the book of background numbers and the number of people. So how many people are there having this background number? And this is this study was made in 2011. Okay, this is quite old study. Well, connectedness in undirected graphs. So an undirected graph is called connected if there is a path between every pair of vertices. Okay, we choose any pair of vertices. If there is a path between every pair, or we can find the path between every pair of vertices, then the graph is called connected. And right now we are talking about undirected graph. Undirected graph is called connected if there is a path between every pair of vertices. An undirected graph that is not connected is called obviously disconnected. So we say that we disconnect a graph when we remove vertices or edges or both to produce a disconnected subgraph. So we can have a subgraph, well, disconnected subgraph, connected graph. Now there are two graphs, G1 and G2. So G1 is a connected graph because let's start with A and let's choose another vertex. We have to choose a pair. So well, let's start with A with any pairing with any vertex of the graph. Rest of the vertex in the graph, vertices in the graph. So AB, there is a path of length 1. A, B, C, there is a path of length 2, even A, there is a path of length 1. So we can find a path. So A, B, C, D, there is a path again. A, B, C, D, E, there is a path again. A, B, C, D, F, there is a path between A and F. A, C, F, G, so there is a path between A and G. Similarly, you can check that this path is connected because for every pair, in the graph, every pair of vertices in the graph, there is a path, right? So this is the connected graph, but this is not connected because we cannot find a path between A and F. Okay, so this is not connected. Okay, there is a result which is theorem in your book. Don't need to prove this, but you just have to remember this result. There is a simple path between every pair of distinct vertices of a connected undirected graph. Okay? Simple path means we don't use an edge multiple times, right? Connected component. This is an interesting concept. A connected component of a graph G is a maximal connected subgraph of G, a connected subgraph that is not a proper subgraph of another connected subgraph of G. A graph G that is not connected has two or more connected components that are adjacent and have G as their union. So there is an example of connected components. This H graph is a union of H1, H2, H3, and H1, H2, H3 are not connected with each other, so they are disconnected. So these are called the connected components. these disconnected subgraphs are connected because the supergraph contains all these disconnected subgraphs. So that is why these are called the components of connected components. But these components are connected, these subgraphs are connected, but on the whole, graph is not connected, supergraph is not connected, but its subgraphs are connected. So the number of connected number of subgraphs which are connected within, but they are disconnected with each other, is the component of a graph G. So for example, if we have a graph like this, okay, this is connected, of course, so it has one connected component, okay. Hmm, if we uh, extend it like this is again uh, a connected graph, and it has one component. Now, what if we remove this and this? So now the same graph, super graph is, you may say this is A. Okay. Now it has two connected components, 1, 2, right? Or if we draw this line, okay. Let me draw this line which we removed, and let me remove this. Okay. So again we have two components, two connected components of this graph, right? So this is how we can find the connected components of a graph. Connectedness in directed graphs. So far we were discussing about undirected graphs, now connectedness in directed graphs. So a directed graph is strongly connected if there is a path from A to B and a path from B to A. Whenever A and B are vertices in graph, for every pair of vertices, if there is a path from A to B, there must be a path from B to A, then the graph is called strongly connected, right? And weakly connected graph, if a directed graph is weakly connected, if there is a path between every two vertices, if there is a path between every two vertices in underlying undirected graph, which is the undirected graph obtained by ignoring the directions of the edges of the directed graph. Or we can say a directed graph is weakly connected if and only if there is always a path between two vertices when the directions of edges are ignored, okay, are disregarded. So clearly, any strongly connected graph is also weakly connected, right? Every strongly connected graph is weakly connected, but weakly connected is not always strongly connected. So here is the example of both types of graph, strongly connected and weakly connected. Let's start from G. Okay, let's try a path from A to D. Okay, so we have a path from A to D, right? Now, whether there is a path from D to A, yes, there is a path from D to A as well, right? So similarly, let's try a path from B to E. Okay, B to E. Yes, we have a path from B to E. So what about E to B? This is the path from E to B. Okay, so this is you can check for all the pairs. So G is strongly connected. So whenever we, according to the definition, whenever we have a path from A to B, then there is a path from B to A as well, right? the path is called strongly connected. And since this is strongly connected, this is weakly connected also. Now what about age? Okay, if we have a path from B to A, but we don't have a path from A to B, do we have? We have a path from B to A, but we don't have path from A to B. Okay, so this is weakly connected. Yeah. The subgraph of a directed graph G that are strongly connected but not contain the largest strongly connected subgraphs, that is the maximum strongly connected subgraphs, are called strongly connected components or strong components of G. Similar to the idea of the components we learned in previous slides. So the graph H has three strongly connected components consisting of vertex A, the vertex E, and the subgraph consisting of B, C, D, and the edges B, C, E, D, and D, B. You can try it yourself. Now this is your homework assignment. Okay, next, how can we count paths between vertices? This is very interesting. Uh, let G be a graph. G again, of course, whenever we say G be a graph, this is actually the set of vertices and set of edges. Uh, G be a graph with adjacency matrix A, and we know how to find the adjacency matrix with respect to ordering V1, V2 to Vn of vertices with directed or undirected edges, multiple edges and loops, everything is allowed. Okay, directed edges, it may contain undirected edges, it may contain multiple edges, it may contain loops, everything is allowed. So the number of different paths of length r from Vi to Vj, where r is greater than 0, is a positive integer equal the ijth entry of AR. If we have a adjacency matrix A and we try to find the path of length r from some vertex to another vertex, then this is the ijth entry of AR. AR means we are going to multiply AR times. Okay, this is the simple mathematics, simple multiplication arithmetic. That is, we have to multiply by a by a, how many times? R times. Okay, so AR means this. And we are not going through this proof. You can read it yourself because we are more interested in the application of this. Okay. So let's have a look at an example to understand it better. So there's an example. How many paths of length 4 are there from A to D? So vertex Vi to vertex Vj. So A to D. Okay, A to D. How many paths of length 4? So let's try to find a path of length 4 from A to D. So this is A to B. Then it must be, according to the theorem, it must be the 1/4 entry of 1/4, matlab 1/4 column, sorry, row 1, and so this is the entry. That is, first of all, we have to find the adjacency matrix of G, and this can be done by, this is A, B, C, D order matters, of course. So this is A, B, C, D. Now A is not connected to it because loop is not there. A is connected to B, so that is why 1 is there. A is connected to C, yes, that is why 1 is there. Similarly, A is connected to D, not E. Okay, so that is why 0 is here. Similarly, you can find the entries for this row. B is connected to A, yes. and B is not adjacent to B because there is no loop. Of course, diagonal elements are 0 because there is no loop at any vertex. So this is the adjacency matrix, and now what we have to do, we have to multiply it 4 times. Now you can verify that the A4 is given by this. Now, so according to this theorem, G be the graph and A is a matrix, and everything is allowed. The number of different paths of length R from Vi to Vj is equal to the ijth entry of AR. So we have to find the path, paths of length 4 from A to D. So we have to find the A4. That is, we have to multiply A 4 times. And now why 1/4 entry? Because of this position. That is why I wrote these positions here. AD are connected in this position. So this position in this graph will give us the number of paths. Okay, so let's see, there are a few paths are written, A, B, okay, then A, B, D. So we have to make it length 4. So we repetition is allowed. We are not required to form a simple graph. So A, B, okay, B, A, then A, B. So there are 3 A, B, 1, 2, oh sorry, A, B is already 1. Actually, that was the second. A, B, then B, A. This is the second, then AB is the third, and then this is the length 4. Okay. Similarly, AB, AC, yes, we can go to A, B, AC to sorry, AB, BA to AC 3 and D. So this is another path of length 4. So total we can form 8 paths of length 4 for this graph. So I hope this concept is clear now. So that's all for today. So next time we'll try to cover the rest of the topics in this section. And till then, take care. Bye bye.